Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to derive an expression for the average probability of error of coherent binary frequency shift keying technique. You should note in my previous video, I have already discussed the transmitter and receiver of the binary frequency shift keying technique, and I would highly suggest you to watch that video before you continue this video. If you already watched that video, let us start with the derivation. As we know, in a binary FSK system, symbols 1 and 0 are separated or distinguished from each other by transmitting one of the two sinusoidal waves that differ in frequency, and hence the name frequency shift keying. Now, we should also note the difference in frequency is given by a fixed amount. Let symbol 1 be represented by S1 of t and symbol 0 by S2 of t. So, the form of S1 of t is equal to square root of 2 EB by TB cos 2 pi F1t, where t varies from 0 to TB. Similarly, S2 of t is equals to square root of 2 EB by TB cos 2 pi F2t. Please note, since it is a frequency shift keying technique, the two signals S1 of t and S2 of t differ with respect to their frequency. Further, EB stands for the transmitted signal energy and TB stands for the bit duration. The values of the frequencies of the carrier, which are F1 and F2, can be given by F1 equals to NC plus 1 by TB and F2 equals to NC plus 2 by TB, where NC is any integer. Now, by looking into equations 1 and 2 carefully, we will see that the signals S1 of t and S2 of t are orthogonal in nature, but however, they are not normalized to have unit energies. So, the orthonormal basis functions for binary FSK system will be given by phi 1 of t equals to square root of 2 by TB cos 2 pi F1t, phi 2 of t is equals to square root of 2 by TB cos 2 pi F2t. Therefore, the coherent binary FSK system is characterized by a two-dimensional signal space with two message points S1 and S2 located at S11, S12 and S21, S22 respectively. Let us now find out the coefficients S11, S12 as well as S21 and S22. Instead of having four different equations, we have tried to accommodate all of it in one single equation, which is the equation for the coefficient Sij, which is of the form integral 0 to Tb Si of t into phi j of t dt. Let us find S11 first. So, S11 is equals to integral 0 to Tb S1 of t into phi 1 of t dt. Now, S1 of t is given here, phi 1 of t is given here. You are supposed to assume I and j as 1 here. Except for square root of EB, the remaining part is absolutely common, that is square root of 2 by TB cos 2 pi F1t. Similarly, we have square root of 2 by TB cos 2 pi F1t. Now, we will note that the orthonormal basis function phi 1 is of the form square root of 2 by TB cos 2 pi F1t. Now, we have the same part appearing twice here. So, I can write it as phi 1 square of t. And then applying the integral, we have integral 0 to Tb phi 1 square of t dt, which is nothing but the energy of the signal phi 1 of t. Now, as we already have said, phi 1 of t and phi 2 of t are orthonormal, which in fact means they have unit energy. So, when I is equals to j, Sij will reduce to root of Eb, and when I is not equal to j, Sij reduces to 0. Therefore, we can write S11 and S22 as square root of Eb, whereas S12 and S21 will be 0. This I have written in this equation 7 and 8 representing the signal vectors S1 and S2. Now that we have found out the coordinates of the signal points S1 and S2, let us move on towards the signal space diagram. As previously said, the binary FSK system has a two-dimensional signal space represented by phi 1 and phi 2 axis respectively, and the coordinates of the first message point S1 is root EB, 0, which will appear at a point of root EB on the x-axis, whereas for the second message point S2 it is 0, root EB, it will appear at a distance of root EB on the y-axis. Let us now assume that the binary symbols 0 and 1 at the input occur with equal probability. Therefore, to realize the decision rule as to whether symbol 1 or symbol 0 was sent, we must partition the signal space as shown in the diagram here into two equal parts. The first region, which is represented by Z1 here, is a set of all points that are nearest to the first message point at plus root EB on the x-axis, and the second region is the set of all points that are nearest to the second message point at plus root EB on the y-axis. As I already said, these regions are marked Z1 and Z2 respectively. Therefore, now the decision rule is simply to guess symbol 1 or signal S1 of t was transmitted if the received signal point falls inside region Z1. On the other hand, decide in favor of symbol 0 or signal S2 of t was transmitted if the received signal point falls in region Z2. Please note, in doing so, two types of erroneous decisions are likely to be made by the receiver. The first type of error is also called as the first kind of error, which is symbol 0 is transmitted, but the channel noise W of t is such that the received signal point falls inside region Z1. Therefore, the receiver decides in favor of symbol 1. On the other hand, we have the second kind of error, in which symbol 1 is transmitted, but the channel noise is such that the received signal point falls inside region Z2, and therefore the receiver decides in favor of symbol 0. We refer to these conditional errors as the first kind and second kind respectively. Let us now move on towards the receiver. Let us start by saying the received signal be denoted by x of t. Now, as we have previously said, there are two orthonormal basis functions at the transmitter. Therefore, the received signal point, which is also called as the observation point, will have two elements given by x1 and x2. I can write expressions for x1 and x2 just like what I have done for Sij, that is by using the second equation in the Gram-Schmidt orthogonalization. X1 equals integral 0 to Tb x of t into phi 1 of t dt, and x2 is equals to integral 0 to Tb x of t into phi 2 of t dt. Now, the form of x of t depends upon which symbol was transmitted. For example, if the transmitted symbol is symbol 1, then x of t is equals to S1 of t plus W of t, where W of t is a sample function of a white Gaussian noise of mean 0 and power spectral density equal to N0 by 2. On the other hand, if symbol 0 is transmitted, x of t equals S2 of t plus W of t. Coming back to the constellation diagram, we previously have said the signal space is partitioned into two regions labeled Z1 and Z2. Accordingly, the receiver will decide in favor of symbol 1 if the received signal point represented by the observation vector x falls inside region Z1. This is the correct decision. Transmitted symbol is 1, the received signal point falls inside region Z1. However, we should note the received signal point will fall inside region Z1 if and only if the value of x1 is greater than x2. This is very important in decision making in binary FSK system. On the other hand, when x1 becomes lesser than x2, then the received signal point will fall inside region Z2. So, the receiver will now decide in favor of symbol 0. Therefore, the decision boundary in the constellation diagram can be given by the equation x1 equal to x2. Now, you should note we have previously derived an equation for the average probability of error for binary PSK. However, in that particular derivation, we had only one element in the observation vector. Here we have two. So, the overall computations, if I take both of them into consideration, will become highly complex. In order to eliminate this complexity, we are going to reduce the dimensionality of the complexity by defining a new Gaussian random variable, which will be the difference between x1 and x2, which I have done here. So, let a Gaussian random variable capital L, which has a sample value of small l, be the difference between the coefficients x1 and x2. So, L equals x1 minus x2. By performing this operation, we have eliminated the complexity of the rest of the derivation by a large amount. So what I will now do is, instead of finding the likelihood functions for x1 and x2 separately, I will find the likelihood function for the variable L, which stands for the difference between x1 and x2, which in fact I have done here. You should note, whenever symbol 1 is transmitted, the Gaussian random variables capital X1 and capital X2 will have values given by root EB and 0. This can be verified by looking at the vector for S1 here. Please note, S11 and S12 are root EB and 0. Therefore, the component X1 when symbol 1 is transmitted will be equal to root EB, whereas X2 will be equal to 0. So, the conditional mean of the random variable capital L when symbol 1 is transmitted is given by expectation on capital L given 1 is equal to expectation of capital X1 given 1 minus of expectation of capital X2 given 1. Now, expectation of x1 given 1 is equals to root EB, whereas expectation of x2 given 1 is 0. Therefore, the conditional mean of the random variable L when symbol 1 is transmitted is equals to plus root EB. In a very similar fashion, we can also find out the conditional mean of the random variable L when symbol 0 is transmitted, which is given here. Please note, expectation of capital L given 0 is equals to expectation of x1 given 0 minus expectation of x2 given 0. In order to fill values here, I will once again go back to the vector S2, where S21, S22 are 0 and root EB. So, I will come back and substitute these as 0 and root EB. So, this is 0, this is root EB. So, mean of the random variable L given symbol 0 was transmitted is equal to minus root of EB. Then we will find out the variance. So, variance of the random variable capital L is equal to, as per the equation here, variance of the variable x1 plus variance of the variable x2. Please note, we have taken a plus here. This is because the random variables x1 and x2 are statistically independent. So, I will simply substitute for variance of x1, which is n naught by 2, and variance of x2, which is also equal to n naught by 2. Therefore, the variance of the random variable L is equal to n naught. We are now ready to find the probability of error of first kind and second kind respectively. In fact, I will start with probability of error of first kind, which is PE of 0. For that, I will assume symbol 0 is transmitted. Now, I will write an equation for the likelihood function, which is also called as the conditional probability density function for the random variable capital L, which is of the form FL of L given 0 equals 1 divided by square root of 2 pi into variance of L multiplied by exponential of minus 1 by 2 into variance of L multiplied by L minus mean value of L whole square. This is the generic equation for Gaussian distribution. Now, let us substitute for variance of L as well as mean value of L as per our previous discussion. Please remember, we have assumed symbol 0 is transmitted. So, when symbol 0 is transmitted, the mean value is minus root EB, whereas variance is n naught. Let me now substitute these values into the equation. So, it is 1 by square root of 2 pi into n naught into exponential of minus 1 by 2 into n naught multiplied by L minus of minus root EB whole square. After simplifying this, I will get the expression as 1 divided by square root of 2 pi n naught into exponential of minus 1 by 2 n naught into L plus root EB whole square. Now, we have the likelihood function, which is also equal to the conditional probability density function for the random variable L given symbol 0 was transmitted. Now, to find the probability of error, we need to now integrate the likelihood function over the region Z1. So, what I will now do is I will take PE of 0 is equal to probability that L greater than 0. Now, why I should take L greater than 0 is because I am trying to find the probability of error. Please note, we have transmitted symbol 0 and the receiver has decided in favor of symbol 1. And as we have previously said, deciding in favor of symbol 1 is nothing but the value of x1 greater than the value of x2. Now, since x1 minus x2 is equals to L, when x1 is greater than x2, the value of L is always greater than 0. That is why instead of writing x1 greater than x2 here, I would directly written it as L greater than 0. So, the probability of error is equal to probability L greater than 0 provided symbol 0 was transmitted. This indicates the error. This is nothing but, as I previously said, integrating the likelihood function, which I have written here. So, Pe of 0 is equals to integral 0 to infinity FL of L given 0 dl. I will now substitute equation 15, which is in fact for the conditional probability density function, into equation 16, which will give me this equation. Now, just like what we have done for the probability of error derivation for binary PSK, we will change the variable from L to Z. So, what I am going to do is, I am going to take the square root of contents of the exponential function except for the negative symbol as a variable Z, which is given here. So, Z is equals to L plus root EB divided by square root of N naught. Please note, I am taking the square root of contents of the exponential function except for the negative symbol. So, now that I have changed the variable from L to Z, I need to now find the new limits of integration. In order to get them, I will substitute the old limits of integration into this equation, which for the lower limit of L equals to 0, we will find Z is equals to square root of EB by 2N naught. The upper limit is infinity previously, so when I substitute that into this equation, I will find Z is equals to infinity. Finally, you should also note we have a component dl. To find dl, I will differentiate this equation with respect to L. So, dz by dl is equals to, since root EB is a constant, what will remain is only L by square root of 2N naught. After differentiating that, I will only obtain 1 divided by square root of 2N naught. Now, since I want the dl, I will simply rearrange this equation to get dl equals to dz into square root of 2N naught. Now, after finding the new integral limits as well as the value of dl, let us now substitute all of these back into equation 17. Please note, the integral limits are to be changed as well as the value of dl has to be replaced. And since the square root of the contents of the exponential function except for the negative symbol is taken as z, this complete term will become minus z square, which is given in equations here. So, Pe of 0 is equals to integral, lower limit is square root of EB by 2N naught, upper limit is infinity, which is given here, followed by 1 divided by square root of 2 pi N naught into exponential of minus z square into dl. dl is equals to dz multiplied by square root of 2N naught, which is given here. So, I find I have a square root of 2N naught in the numerator here and a square root of 2N naught in the denominator. I will cancel them out. So, what remains is integral with the respective limits 1 divided by square root of pi exponential of minus z square dz. Let me now take 1 divided by square root of pi towards the constant term. So, the probability of error of first kind, which is P of 0, is now given by 1 divided by square root of pi integral square root of EB by 2N naught to infinity exponential of minus z square dz. Now, very importantly, we will now compare the equation for the probability of error for the first kind with a standard function, which is the complementary error function, which is given in the form ERFC, which stands for complementary error function of u is equals to 2 divided by square root of pi integral u to infinity exponential of minus z square dz. As I said, let us now compare it, and by careful observation, we will find that I can write Pe of 0 in terms of ERFC as Pe of 0 is equals to 1 divided by 2 into ERFC of square root of EB by 2N naught. Now, it is quite easy. All you need to write inside the brackets here is the lower limit of the integral before you compare it with ERFC function. Right. So, this is the final expression for the probability of error of the first kind. Now, by using a very similar approximation, you will find the probability of error of second kind, which is Pe of 1, also to be exactly equal. Let us now move on to find the average probability of error. The equation for average probability of error is given by P naught into Pe naught, where P naught is the a priori probability of symbol 0, and we have later P1 into Pe1, where P1 is the a priori probability of symbol 1. Now, these are, as we already have said, a priori probability of symbol 0 and 1 respectively. Now, I have previously said many a times that the probability of generation of symbol 0 and symbol 1 are equal. Therefore, P naught equals to P1, which is equals to 1 by 2. Further, we also note that Pe naught is equals to Pe1. We have already shown it here. Therefore, the average probability of error will be equal to Pe of 0 as well as Pe of 1. Therefore, we can now conclude by stating that the average probability of error for coherent binary frequency shift keying technique is given by 1 by 2 ERFC of square root of EB by 2n naught. Right. That is about the derivation for average probability of error. If you like this video, kindly press that like button and subscribe to my channel for more videos on digital communication. Thank you for watching. Have a good day.